In this video, we're going to talk about the change of basis matrix. So to introduce what this is, let's just recall some facts. So let's say that V is a finite dimensional vector space over a field, let's say the real numbers. Right? So V is some finite dimensional vector space over, say, R. And if you have a basis, say B, for V, say an ordered basis, V1. So let's say that V is n-dimensional, so every basis will have n elements, right? So you have a linearly independent set of n vectors and ordered, and this spans V, so you have n linearly independent vectors. Okay, that's an ordered basis for V. Well, when you have one of those, this defines a map from V to Rn that takes a vector in V and maps it to the coordinate vector of V relative to the basis B. So you can have this picture. Well, let me just introduce some more notation before I do an example. Let's say that, okay, so once you have a basis, you get a way of describing the vectors in V as coordinates, right? Coordinate vectors in Rn. Now let's say that I have another basis, another ordered basis C, script C, right, curly C, which is W1 through Wn. So let's say that you have another ordered basis for V. Well, then you get a map from V to Rn that sends V to the coordinate vector of V relative to the basis C, right? Well, so once you have these two bases, you're going to have two different coordinate vectors, and now the question is, how do you relate this first coordinate vector to the second coordinate vector? So let's just do a little picture. So let's say that V is some subspace of R3. Again, let's just make V some plane, right? So that's V, it's a two-dimensional space. And let's say that I have some basis V1, V2, and that's my B. So B is the basis, the ordered basis V1, V2. Then that gives me a linear transformation from V to R2. It's actually an isomorphism from V to R2. Okay. And V1, let's just remind ourselves that the coordinates of V1 relative to B is just E1, right? So the coordinate of V1 relative to B is just the vector 1, 0, and the coordinate of V1 relative to V2 relative to B is 0, 1. Okay, and let's say that I have another basis W1, W2. Then I get another map from V to R2 that takes W1 to 1, 0, and W2 to 0, 1. Because remember, the way you define the coordinate vector is you say how many of each basis vector you need. So for V1, the reason why the coordinate vector is 1, 0 is because V1 is 1 V1 plus 0 V2. And similarly for V2, W1. Right, W1 is 1 W1 plus 0 W2. W2 is 0 W1 plus 1 W2. So that's why the coordinates are the way they are. And if you just take a vector V, let's say here, okay, then that will go to like some vector here, and then it'll go to some other vector. So this is V relative to B, And then in the other basis, it'll go to some other vector in R2. So let's see. How do you describe V as a combination of W1 and W2? Maybe it's going to be like a bunch of W2s and then minus some W1s, I think. So it's, I think if I wanted to make my picture accurate, V would be something like that. I don't know. Okay, so here's V relative to the basis C, the coordinate vector. And the question is, how do I relate this vector and this vector? You know, a good analogy to this would be like, if you have, okay, it's an analogy, right? So pretend that this is like something that you're trying to measure the temperature of, and this person uses Fahrenheit and gets some number, like 10, and then someone else uses Celsius and gets a different number. And how do you relate those two numbers together? Well, there's a conversion, right? You can take 9/5 C plus 32 converts you from Celsius to Fahrenheit. And then if you reverse that, you can get from Celsius to Fahrenheit. If you reverse that, you can get from Fahrenheit to Celsius. Well, that's, right, you're taking the same vector. It's just that the way that you're describing that vector with coordinates is going to be different depending on which basis you use. And so it's natural to ask, well, okay, how do you connect the two coordinate representations, the two coordinate vectors together? And what we're looking for is a matrix that will, when you multiply by the coordinate vector of V relative to B, gives you the coordinate vector of V relative to C. Okay, let's just kind of explain for clarity why there is a matrix, why there is a linear transformation that takes you from the first R2 to the second R2. The reason is because a choice of a basis, so this map from V to R2, right, this is an isomorphism. This is a one-to-one onto linear transformation. And when you have an isomorphism from one vector space to another vector space, then the inverse map that takes you from the coordinate vector to the original V, that is also an isomorphism, and it's a linear transformation. It's an isomorphism. It's a linear transformation that is an isomorphism. That's the correct way to say it. So you have an isomorphism from the first R2 to V, and then this map from V to the second R2 is also an isomorphism. And so this map that we're interested in is the composition of these two maps, where you take the first R2, you map it to V, and then map V into the second R2. That composition is an isomorphism. And that's, so when you have an isomorphism from R2 to R2, that's given by a matrix, right? And any linear transformation from Rn to Rm is given by a matrix, and that's the matrix we want. So we have this isomorphism T, and it's this isomorphism, so this is a map from R2 to R2 that maps the coordinate vector of B to the coordinate vector of V relative to B to the coordinate of V relative to C. This is an isomorphism. Okay, an isomorphism, so i.e. a one-to-one and onto. In other words, invertible, right? Invertible linear transformation. And when you have an invertible linear transformation from Rn to Rn, it's given by an invertible matrix. So there is a matrix associated with T. And what we're looking for, remember we saw that whenever you have a linear transformation from one vector space to another vector space, and you choose bases for the domain and codomain, you get a matrix from it. So what we're looking for is, we're looking for the standard matrix of T. Okay. Well, okay, so let's think about what that is. So the standard matrix of T is the matrix whose columns are T of E1 and T of E2, right? Well, what's that? Well, what's T of E1? Remember, E1 is 1, 0, and that's precisely the coordinate vector of V1 relative to the basis B. And so T of E1, right? T of E1, well, that's T of 1, 0, and that is precisely T of the coordinate vector of V1 relative to B. Well, okay, what does T do, though? It takes, T maps the coordinate with respect to B to the coordinate with respect to C. And so T of this element, because it's a handful to say, okay, it's a mouthful to say, is going to be V1 relative to the basis C. And similarly, T of E2 is T of, by definition, 0, 1. And that's going to be T of, so remember, 0, 1 is the coordinate vector of V2 relative to B. Okay, so this is T of the coordinate vector of V2 relative to B. And that, by definition of T, is the coordinate vector of V2 relative to C. And so therefore, this matrix is precisely the matrix whose columns are the coordinates of V2 relative to C and V2 relative to C. Okay? And so in general, the change of basis matrix, the matrix that sends, say, Vi relative to B to Vi relative to C is precisely the matrix the n by n matrix whose jth column for j equals 1 through n is the coordinate vector of Vj relative to the basis C. So it's V1 relative to C up to, okay, the arbitrary one is Vj up to C, and then the last one is Vn up to C. And Vn relative to C, and this is an n by n matrix. Okay? And this is called, this matrix is called, the square matrix is called the change of basis matrix from B to C. It converts vectors written relative to B to the way a vector is written relative to C. Okay, and some notation for this, often denoted, it's not always, but it's often written like this. A P and then B to C. This notation. Yeah, or the change of basis matrix or change of coordinates matrix. So let's do an example let's say, now I'm referring to the book by Lay, section 4.7, Lay's Linear Algebra textbook. So let's do an example. Let's say that B is a B1, B2, and C is C1, C2. Oh, they write it as a set. Okay, well, it should be this should be ordered. He's a bit imprecise, so I should say let these be ordered bases for the vector space V. And suppose that B1 is 6C1 minus 2C2, and B2 is 9C1 minus 4C2. Okay. Part A, find the change of coordinates matrix. Oops. Find the change of coordinates matrix from B to C. And then part B says, find XC for X equals negative 3B1 plus 2B2. Okay? So that's the question. Well, why don't you take a minute and work on it and see what you get. Okay, let's go over the answer. So for part A, remember the change of coordinates matrix from B to C is just so my basis is B1, B2, and I want it relative to C1 and C2. So I'm looking for the matrix which is, the matrix's first column is B1 relative to C, and then the second matrix, the second vector is B2 relative to C. So I have to find these two coordinate vectors, and then once I have those two coordinate vectors, those are going to be the columns of the matrix. So, well, you're given that B1 is 6C1 minus 2C2. So we have B1 is 6C1 minus 2C2. That's the same as saying that the vector of B1 relative to C is 6, negative 2. Right? That's the definition of the coordinate vector. And similarly, B2 is 9C1 minus 4C2, so that tells me that my basis vector, that my vector of B2 relative to C is 9, negative 4. Yeah, this is a negative 2. And so therefore, my matrix, the change of basis matrix from B to C is just this matrix, 6 minus 2, and then 9 minus 4. So that's the answer to A. Okay, part B. Find, so this is the coordinate vector of X relative to C for X equal to this. Well, okay, so this matrix takes the coordinate representation of X with respect to B to the one with respect to C. And so we're given that X is equal to this. So that means, let me just write that down. So when X is negative 3B1 plus 2B2, that's the same as saying that the vector X relative to B is equal to negative 3, 2. And so therefore, and we know that X with respect to C, that's equal to the matrix, the change of coordinate matrix from B to C times the vector of X relative to B. And so this is equal to this matrix times this vector, and that is equal to, okay, that's negative 18 plus 18 makes 0, and then 6 minus 8 is negative 2. And so the answer is negative 2. And let me just check in the back of the books. I'm doing 4.7 number 1. Yep, that's correct. Yes. Okay, let's do another one. Let's do number let's do number 13. Let's do another one. For this example, you have to be familiar with the vector space of polynomials. So in P2, find the change of coordinates matrix from the basis B, which is 1 minus 2t plus t squared, 3 minus 5 plus 4t squared, 2t plus 3t squared, to the basis C, which is 1t squared. And then find the B coordinate vector for -1 plus 2t. Okay, so to do this problem, you have to be familiar with what P2, what this notation means. It means all polynomials with degree less than or equal to 2. And so find the change of coordinates matrix. So again, so let's call this B1, B2, B3. We want to write this in terms of C1, C2, and C3. Well, we have that B1 is 1C1 minus 2C2 plus 1C3, right? So B1 relative to the basis C is just 1, -2, 1. Similarly, B2 is, okay, it's 3 minus, this should say 3 minus 5t. So it's 3 minus 5t plus 4t squared. This is B2 relative to C. And then B3 relative to C is, so B3 is 0 plus 2t plus 3t squared. And so the change of coordinates matrix from B to C is the matrix with these 3 columns. So the first column is 1, -2, 1. Second column is 3, -5, 4. Third column is 0, 2, 3. And then find the B coordinate vector for -1 plus 2t. Okay, so here it's actually asking for the B coordinate vector, right? And so to do that, we can write this polynomial in terms of the basis C. So this polynomial is okay, so let's just call this like P of t. So P of t relative to the basis C is going to be -1 plus 2t plus 0t squared. And so to convert from C back to B coordinates, well, this matrix, right, this matrix that we found takes you from B coordinates to C coordinates. So what matrix takes you the other way around? What takes you from XC back to XB? Well, that would be the inverse, right? The inverse just undoes, it just reverses what the original matrix does. And so we want to evaluate the inverse of this matrix times the vector negative 1, 2, 0. Well, one way to do this is to actually find the inverse of this matrix, but okay, it's a 3 by 3 matrix, we don't want to do that. Instead, right, to find the b coordinate, we're asking what vector does this matrix so maybe a different way of saying it is that this matrix maps V relative to B to V relative to C, right, by definition. And this is an invertible matrix, and so we want to know what the input is that will give us the output that's given in the problem. So we're given that the coordinate vector of P relative to C is this, right? That's our vector V with respect to C. So we're given this, and the question is, what's this? Well, we can just do the elimination. We want to figure out what matrix or what vector gets sent by this matrix to the vector negative 1, 2, 0. So to do that, we can just use Gaussian elimination. Let's see, negative 1, 2, 0. And figure out what the input has to be. So let's do that. So we start from the left and go down, right? So we want to change row 2 to row 2 plus 2 row 1. So that'll give me 0, 1, 2, 0, and then 1, 4, 3, 0. And then we want to change row 3 to row 3 minus row 1. So that will give us this. Okay, so the first column's done. And then I want to convert row 3 to row 3 minus row 2. Zero, zero, 1, 0. Did I do this right? Let's check one more time. Yep, that looks right. Let's check the elimination. Oh wait, this last one isn't correct. This one should be a 1, right? Because it's row 3 minus row 1. So then last one is 0 minus negative 1 is 1. So you get this, and then when you subtract, this is also 1. Okay, so I think this looks correct. And now we go up, so then it's row 2 goes to row 2 minus 2 row 1. So you get, row 2 goes to row 2 minus 2 row 3. So then you're going to get a negative 1 here, right? So. A negative 2. And then this one's going to be a 0. And then the last step is row 1 goes to row 1 minus 3 row 2. So that will give us row 3, let's see, row 1 goes to row 1 minus 3 row 2. So negative 1 minus 3, okay, negative 1 minus 3 times negative 2 is negative 1 plus 6, which is 5. Hooray, we do get the answer in the back of the book. So we get 5, negative 2, 1. So remember, what did this tell us? This told us that the vector relative to b is 5, negative 2, 1. And so that's the answer, right? The question was the coordinate vector. So the b coordinate vector for negative 1 plus 2t is this vector 5, negative 2, 1. Finally. Okay, so that just gives you some examples how to calculate and how to work with the change of coordinates matrix. So let's just do a brief summary of this. This is a long video. So when you have a vector space, we've seen that you can get coordinates once you choose a basis. But if you change when you have two bases, you get two different coordinate representations. And what we're looking for is a matrix that will convert from one coordinate representation to another. That's called the change of basis matrix. And it turns out that what you can do is you can take this matrix, which is formed by taking v1 through vn, and then finding the coordinates of v1 through vn relative to the basis c, and then making those the columns of the matrix. Okay, and then we did some concrete examples. The first example is easy, it just follows from the definition. And then the second example was a bit more involved. It's not too much more involved, but basically we did an example of where you go back, right? We found the b coordinate vector given a polynomial by first finding the c coordinate and then figuring out using the change of basis matrix. This is without actually finding the inverse. We could have found the inverse of this matrix and then multiplied it by negative 1, 2, 0, but it's faster to just use Gaussian elimination to figure out what the vector relative to b is. Using Gaussian elimination, this way you don't have to find the inverse. Okay, so I hope this clarifies section 4.7 of the lay textbook. Oh yeah, and one thing I should probably add before I stop is that this is related. So recall that when you have a linear transformation and you have a basis for the domain and codomain, then you get a matrix from it. Now this matrix, the change of basis matrix, is the matrix of the identity map. So note, of the identity transformation from V to V, so this just takes V to V, relative to the bases B and C. Okay, why is that? Because this matrix, the jth column, right? Because the jth column of this matrix for each j is precisely I of vj relative to c. Okay, and that's precisely what you do to, so here B is V1 through Vn, right? This matrix is precisely the change of basis matrix because it's just Vj relative to C. That's the jth column. And then by definition of the matrix of a linear transformation, right, what you do is you make the jth column equal to T of Vj relative to C. Well, in the case when T is just the identity transformation, V to V, so V and W are equal, you just have the identity transformation, you just get the change of basis matrix. You just get I of Vj relative to C, which is equal to Vj relative to C. So this is actually how it's explained in the book by Treil, Linear Algebra Done Wrong. He says that the change of basis matrix is this matrix of the identity transform. So it's like this would be the notation for it. And so this is the explanation of why. So you can either define the change of basis matrix the way I did, which I think is kind of the most natural way, or you could define it to be the matrix of the identity map relative to B and C. Okay, so that's all I wanted to say for this video. Thanks. Ooh.